All right, hi everyone. I'm Tengxiang Zhang, and I'm from Institute of Computing Technology, Chinese Academy of Sciences. And today I'm presenting the work of my colleague who cannot be here due to visa issues. And the talk is about FewShotBP towards personalized ubiquitous continuous blood pressure measurement. That's a reminder for me. So continuous blood pressure measurement is very important for several reasons. The first is it provides continuous measurement, addressing clinical blood pressure measurement blind spots, such as nocturnal dips or morning surges. It also reduces the white coat effect, which people feel nervous around doctors, which leads to more accurate readings. And most importantly, their data indicates that a large portion of the population is unaware of their hypertension, making it essential for personal health management. So the connections between the physiological signal and blood pressure readings are really complex and personalized. So model personalization was introduced to boost this accuracy, but there are two challenges ahead. The first is we don't have a ton of labeled data to tweak the model, and the second is fine-tuning deep learning models on wearable devices is tricky. So in this paper, the authors highlight the key differences from previous research. The authors evaluate performance in conditions where labeled personalized samples are scarce. The authors paid special attention to how the model performs when fine-tuned on wearable devices. They also address performance on public datasets and real-world datasets. And there's no personalization targets were exposed to the training set. Let's talk about methodologies. And here they also propose two enhancements on the existing transfer learning frameworks. An improved network architecture for model pre-train and a personalization adapter for transfer learning. So the architecture is mainly inspired by the CompNext. The authors CompNexified the rest blocks in the previous hybrid networks to reduce the parameters. They also replaced the fully connect layers with random forest regressor during personalization. Both auxiliary features and neural features are fed into the regressor for personalized blood pressure readings. Let's see the experiment. And so here, we demonstrate the statistics of the public dataset that's used in the paper. And here we show the results obtained in public datasets. And so FewShotBP, which is the green line with square markers, is compared with several baseline models. And the baseline models with personalized adapters are also evaluated for fairness. As you can see, the FewShotBP outperforms the others when the BP model is personalized using 5, 10, 25, and 50 labeled samples. So here we illustrate the blunt Altman plot for the experiment on public dataset. The plot shows there is a standard deviation of 7.3 for SBP and 4.7 for DBP. Now let's show the experiment on subjects. So here's the demographics and distribution on real-world subjects. They exhibit a more significant divergence in data distribution, making few-shot transfer learning even more challenging. So they also recruited 28 subjects, and they are instructed to do a cold pressor test, which is put your hand in a really cold water. And there's also high-intensive exercise and stare test to alter the blood pressure. So here is the experiment settings. And the results show that the proposed method has an advantage in a majority of test cases. And on this page, we present an overlapped blunt Altman plot to provide an intuitive demonstration of the improvement. The green dots representing FewShotBP exhibit a narrower distribution, indicating higher accuracy. Let's talk about major findings. So here the author evaluate all personalization adapted attached networks with and without auxiliary features. A positive bar indicates that PA with auxiliary features performs better. And in their analysis, they assess the impact of various components in two distinct settings as depicted on this slide. In the first scenario, they observed substantial contributions from both the architecture, the modality, and the personalization adaptation. However, in the second scenario, it becomes evident that the primary performance improvement stems from the personalization adaptation, actually. And these findings suggest that replacing fully connected layers with personal adaptation can significantly enhance the accuracy of diverse models with only minor performance distinctions among models. So as expected, FewShotBP significantly outperforms fine-tuning networks in terms of speed. The authors conducted all experiments on CPUs to simulate relative performance. So here are the limitations. So first, in certain instances, as depicted in this figure, the results, which is the green line, deviate significantly from the ground truth, which is the black line. And they conducted a t-SNE analysis on the extracted features and found that they exhibit little distinguishability across various blood pressure labels. So FewShotBP cannot work miracles if the features lack discriminative power. So it implies that the quality of the extracted features are essential for blood pressure regression. Moreover, several inherent limitations are present in the user study. For instance, some subjects may not exhibit sensitivity to the cold pressor test. And also the exercise test introduces a correlation between changes in blood pressure and heart rate. So here's the summary. Well, the first is the complexified network architecture. It reduces a number of parameters and so enhances generalizability. The second is the personalization adapter with auxiliary features leads to better FewShot personalization performance and less computation burden. And also the structure being optimized in the process is the paramount factor influencing accuracy. In this study, the authors employ a random forest regressor. And future work should focus on obtaining better representation on intra-subject blood pressure variations. And thank you for listening. And here's the email of the actual author, and also this is open sourced online, so everyone can find there. Yeah.
Okay. Is he present? No. Ah, okay.